Okay, well, it's time to move on to lesson 3. For unit 1, we're going to talk about momentum and impulse. Now, momentum. As you can see at the beginning here, and again, make sure you guys turn to these particular notes so you can actually highlight as we go along here. You can approximately think of momentum as the difficulty to change an object's motion. And I'll come back to that point in a second. And the equation that actually determines momentum is the equation P is equal to mv. Let's go over a few details about this. So as you guys know, m of course is mass, and mass being a scalar. And typically we have the standard unit for mass is kilograms. V is velocity, which is a vector quantity. And momentum itself is in fact a vector quantity as well. And we use the letter P for momentum. Now there's no kind of official unit for momentum, so we call them derived units. They come straight from mv. So therefore, kilograms meters per second would be the standard unit for momentum, but it doesn't have a special name. Now remember how I talked about it being the difficulty to change an object's motion? Now I have a couple of pictures here to kind of illustrate that point. If you use the formula P is equal to mv, can you see that m and v both have a direct relationship with momentum? So, to have a lot of momentum, you need high mass and a high velocity. And if you have both of those being very high, that would be a high momentum. And that means the object would be extremely difficult to change its motion. For example, we have like a football player, whereas these guys are just huge, 300 pounds, so a huge mass, and they can move really, really quickly. And so very, very difficult to tackle them and change their motion. And of course, when we have this a train type situation, a train has a huge mass and they move very, very quickly. So we definitely recommend you don't put a car in front of those things, because these things will just go right through the car and just keep on moving. Because they have so much momentum, it's really hard to change their motion. So that's an approximate way of understanding what momentum represents. Now we have a related topic called impulse. Now sometimes we use the letter J for impulse. It's not on the formula sheet, but if you want to use a letter for impulse, you can use J. And essentially, impulse is a net force applied over time. And the equation illustrates that. Simply F net times T. And much like momentum, it's a vector, and the units are derived. They are, in fact, Newton seconds. Okay, so these are kind of our two main kind of parts of this particular unit, and they're actually related to each other using something called the impulse momentum equation. Now you guys, the derivation for this equation is actually in your notes. I'm just going to show it to you to make it even clearer, hopefully. It's all going to start with Newton's second law. If we start with F net equal to ma. But if we also have the equation for acceleration, which is equal to change in velocity over time, we can actually combine these two equations. Sorry, I must be getting emotional here. You can bring these two equations together and you end up getting F net is equal to m delta v over t. And you can call it delta t if you wish for a time interval. And then we can cross multiply this and we end up getting F net delta t equal to m delta v. So this equation right here is a special one, because on the left we have something called F net delta t, and we know already that this represents impulse, which, if you wish, takes the letter J. So that part over here is impulse. On the right-hand side, now this looks like mv, and we know that mv is momentum, but it's actually m delta v. And so this specifically is change in momentum. So we call this the impulse momentum equation. And what it says in a very basic sense is that if you apply an impulse, if you apply a net force over time, you will change an object's momentum. Okay, so that's kind of the basic interpretation of it. Now, on your formula sheet, it doesn't quite look like this. It actually looks like what you see here at the bottom. This is what you would have on your formula sheet. F delta T is equal to M delta V. Couple things to remember. One, understand that this F represents F net. Not just any force, it's the net force applied over time. Second point is that both of these are different ways of actually finding impulse. So I'm just going to move this away. These are two different ways of actually finding impulse. So on your formula sheet, if you want to, look for this equation, and right beside it, you can either write J or the word impulse. That's what I really recommend. So that anytime you see the word impulse in a question, you know automatically that this is the equation you're going to go to. And you can see also that impulse can have two different units. You can have Newton seconds, but you can also have kilograms meters per second. So they must be equivalent to each other. Okay, so to finish up the first part of this lesson, let's do an example with the impulse momentum equation. And you can see right off the bat, you see the word impulse right here. And this is good news, because then you can go right to your formula sheet and realize that this means we're dealing with F delta T equal to M delta V, and both of these are equal to impulse, or you can write the word impulse if you don't like the letter J. So there's our impulse momentum equation. And if you want for this one here, you could make a list of what you're actually given. So I'll do that on the side here. Why not? Whatever color. What color do you use? Okay. So, and by the way, I'm just going to move this over a little bit. I think I made that a little too close to that side. The magic of technology. Okay. So we know that the mass is 700 kilograms. So let's put that over here. So mass is 700 kilograms. We know that originally it's moving at 58 kilometers per hour east. Hey, let's do the conversion right now. Do you remember we want to convert this to meters per second? Do you remember we're simply going to divide that by 3.6. And that will represent the V initial. So let's take 58, divide that by 3.6. So 16.11 approximately. So 16.11 meters per second. But again, it's towards the east. It's a vector quantity. So let's establish a clear reference system somewhere in this solution. So again, I'm just going to do a little redecorating here. I'm going to move this down a little bit so I have room for a formula, for a reference system. Let's choose up here at the top that, let's say that east is positive and west is negative. So make sure you include your reference system. These are vector quantities. That means your V initial will be positive 16.11 because it's going towards the east. Good. Then we have the impulse, and that's going to be, notice it's 30 kilonewtons seconds. That's not the standard unit. We want to convert that to standard unit, so kilo means 1,000. That's going to be 30,000 newton seconds. And notice it's going towards the west, so that's going to be negative. And what we're looking for in this question is the final velocity. So if it makes it easier for you, you can make that list on the side. Most important thing is you can convert to standard units and put the positive and negatives in here. All right, well, we know the impulse, we know the mass. Notice, by the way, there's no force and time information in here at all. So how about we get rid of that then? So we're going to eliminate the whole F delta T. We actually don't need it. We know the impulse and we know the mass. So why don't we find the change in velocity. So let's do delta V equal to J over M. So that's going to be negative 30,000 divided by the mass, which is 700. So that's going to give us negative 42.857 meters per second. So that's the change in velocity, but we're looking for the final velocity. So, you guys remember we have delta here. Do you remember what delta is when you expand it? What minus what? Answer, delta V will be equal to V final minus V initial. So we're solving for V final. Let's get that by itself. So V final becomes equal to V initial plus the change in velocity. So V initial is 16.11, and then I'll be adding that to negative 42.857. And for sig digs here, looks like we have 3 significant digits. So that comes out to be 26.7. So negative 26.7 meters per second. Let's interpret that. That's 26.7 meters per second. And negative, based on our reference system, is west. Done. Okay, so just a couple of reminders. Whenever you see the word impulse, you should be happy because there's only one equation on your formula sheet that actually deals with that. And that's this one right here. So you just write out the impulse momentum equation. Make sure you write equal to impulse. And then also just don't forget to use standard units and don't forget to use a reference system. And then you're good. Okay, so we'll stop it there and we'll continue the rest of this lesson in our next slide, our next video.